So, welcome everybody to today's webinar by the IEA SHC Solar Academy on the topic of low carbon, high comfort integrated lighting. My name is Ellen. I'm a representative of the International Solar Energy Society team here in Freiburg. ISIS is the technical host of this event, and I will start by giving you a short introduction to ISIS and the work we do, and then we will get started with the webinar. So ISIS is an UN accredited membership NGO. We were founded in the 1950s, have been UN accredited since 1992, so we have been around for quite a while. And nowadays we have a diverse international membership with members from 110 countries to be exact. And our mission is 100% renewable energy for all, used efficiently and wisely. And to achieve our mission, we have quite a lot of activities going on. For one, you've probably heard about our conferences. We have, for example, the Solar World Congress. The banner that you can see on the slide is from last year's conference. The next one will take place in 2027. And then we also have our Eurosun conferences. The next one will be held this year in Freiburg in Germany from the 14th to the 18th of September, but more about that later. We also do webinars, such as the one today, and we have education initiatives. We also have two major publications. One of them is the journal Solar Energy, which you might be familiar with. And then additionally, we also do infographics, and we even have an online solar energy museum. So we are deeply committed to advancing the dissemination of solar energy. You joined us for a webinar today. And of course, this includes a Q&A session, which is one of the most important parts of that webinar. So we will start with presentations from our four speakers. And then while that is going on, you can submit your questions in writing via the Q&A chat box in Zoom. And then at the end, we will have a cumulative Q&A session. And please keep your questions short and precise so we can work with them in an easy way. And with that, I'm happy to introduce you to today's moderator, Bärbel Epp. Bärbel is the founder and managing director of the consultancy Solrico, and she's also responsible for the newsletter of the web portal Solar Thermal World. And she will be moderating today's event and will be taking in all your questions. And with that, I'm happy to hand over to her. Bärbel, thank you for joining us today, and the floor is yours.
Yeah, Ellen, thank you very much. I'm happy for another webinar of this series, Solar Academy. And I would like to introduce you the IEA Solar Heating and Cooling program first in some slides. And I will share my screen and start presenting. Yeah, so what is the IEA Solar Heating and Cooling Program? It's a project-focused international R&D collaboration, also fairly old. We have 15th anniversary this year and next year. 19 member countries, which are marked orange in this map, are members. The EU Commission plus 7 international organizations are sponsored, which are marked green here. More than 200 experts group in this what we call Task, which are like research platforms. And we have currently 7 of them running on different subjects, which I have listed here. It's like PVT heating systems. We have 2 on solar thermal energy storages, 1 on life cycle and cost assessment for heating and cooling technologies, 1 for solar photoreactors looking into fuel production and chemicals. Then there's 1 solar hot water for 2030, almost at the end. And then the one which is organizing today's webinar, which is the task on high comfort integrated lighting. So how does it work? If you want to participate in the task work, you should check on our website whether your country is a member or an organization member via the sponsors. And then you can look into the task website. Each task has on the IEA HSC global website its own subpage. And there you find the contact information for the task manager. And with him or her, you can discuss your interest and expertise. So what is the IEA SHC Solar Academy? offering you. We would like to stress that we do not just have scientific results like reports or scientific papers, but there's also a lot of training material available. And often it's case studies like we will hear today as well, fact sheets or databases, and even tools are part of the task work. So the Academy offers these regular webinars with ISIS. The next one will be held in June, on the 15th of June at 4 p.m. The subject this time is district heating, and it will be announcement for the two conferences coming up this September, Eurosun and Solar Paces. All these webinars are always held once at 2 GMT and rebroadcasted a second time at another day at 5 GMT. You find all the previous recordings under this on our website, under this link. And also, it's important to say that we offer online trainings, on-site trainings, in member countries on request of these member countries. And past trainings have taken place in China, Cape Verde, United Kingdom, and South Africa. Some more links and how to find things. Here, there's the general website. Then there is a special section on the website for publications where you find the link here. We are in LinkedIn and on YouTube. And if you have particular questions, you can contact the Secretariat. Two flagship publications. There is the Solar Heat Worldwide report, once a year published. The latest edition is from June last year. It's a very good summary on global data, regional and national data, as well referring to technologies in solar heating, but also in terms of application. And then there is a semi-annual newsletter published, so the Solar Update, with its latest version from January 2026, which can also be found at the website. So, and this is already the end of my short presentation. I would like to introduce you our first speaker, which is Jan de Boer. He is also task manager of Task 70, the one which is organizing the webinar today. He is group manager, lighting technology and passive solar systems in the Department of Energy Efficiency and Indoor Climate at the Fraunhofer Institute of Building Physics in Stuttgart, Germany. And he has built up a strong research network on this topic across the globe because he has been running tasks since 2013 already. So he will give us the status of lighting and decarbonization in the first introduction presentation. Jan, I'm looking forward to your presentation.
Yes, Bärbel, thank you very much for the kind introduction. Just trying to share my screen here.
Oh, I have to stop mine probably. Does it work? Ah, now it's coming.
It's coming? Okay.
Yeah. Yeah, we're getting there. Good. We see your first slide.
Okay,
Perfect.
perfect.
In presenter mode.
Okay,
Perfect, Jan.
Yeah, thank you. So it's a pleasure to introduce to you this joint research task, low carbon, high comfort integrated lighting. And today's talk is going to be basically split into two parts. On the one hand side, I'm going to give you an overview of the whole research project. And then in the second part, I'm going to dive a little deeper into the part of the title, which is on low carbon lighting. So first of all, talking a little about what motivated us for this activity. We are still seeing in lighting an increase in intensity worldwide by around 2% each year. We know that electricity for lighting accounts for around 5% of the global greenhouse gas emissions, and from the electrical energy consumption side, we are at around 15%. More and more, we are going by ordinances, by political will to reduce the carbon content in all the processes. So decarbonization by 2045 or 2050 is in many countries a goal we are aiming at. In this context, we are, of course, then seeing quite some restrictions on CO2 emissions coming up. We are seeing a higher competition for electricity as well if we're addressing electric lighting, and that all brought us to start to look on a wider perspective into lighting solutions. So far within IEA, we had focused quite strictly on the energy side, and we're trying to widen the perspective here on the whole life cycle chain, and introducing here embodied carbon rating, operational carbon rating, things like that, trying to understand that better. For electric lighting as well as for daylighting technology, we're trying to incorporate into our research regional energy market aspects, trying to address that, and also looking at, of course, at the interaction with other building trades. Where are we technology-wise at? I think we all know and have seen that the LED transition on lamp level is generally performed. We are having highly optimized, highly industrialized products here. It's a little different on luminaire level side. So there are still some potentials for decreasing embodied energy. If you're looking at modular luminaire architectures, direct integration of components into of lighting components into building components and architecture. We are seeing some new task lighting concept, and of course, retrofit solutions are out there, which can be quite efficient. Then looking at the facade, at the daylighting side, it is in the core aspects basically about reducing masses in the facade. There are technical solutions here, at the brink of going stronger into the market. If we're looking at how we can cope with sun shading or glare, smart glazing systems are out there, vacuum glazing, so that all gives us new chances and opportunities to reduce basically the masses in the construction. On the right-hand side, you're seeing another component driver here is that more and more recycled components are used. What you're seeing here by a reduction of 40% is a comparison of standard glazing by low-carb glazing, which you by now get from the bigger manufacturers, as they are using more and more recycled glass in their manufacturing facilities and processes. We have other aspects to address in this project. Of course, the architectural and design constraints. We have to sort of guarantee and look for a good daylight supply in the more and more dense urban environments. We have to understand facades not only from the inside, but from the outside as well. And it is sort of a competition we're seeing for limited building envelope areas. So it's not one against the other, but more it's a negotiation of, for instance, daylight coming into a building versus active solar on facades or facade greening we're seeing. So these are things we have to be aware of in the design processes. Last but not least, actually first, we have to look at the user expectations and the user requirements. That is what we are designing buildings and spaces for, to fulfill the requirements and needs of humans. And this has seen quite some new findings, discoveries over the last decades on the visual perception side, but also on the non-visual effects of light. And that is on the one hand side to be addressed in itself, but also, of course, has quite an impact on driving innovations in lighting technology. So that gives us sort of the content framework and how can we empower things like that. We have to look at the digital processes which sort of go along with this whole lighting value chain, as we have called it. And here IEA work has always been quite strong on software side over different tasks we had over the last decades. It's on the photometry side, it's on the rating tool sides. Standardization processes have been triggered here, and that is something we are intending to continue in this project as well. You're going to hear more about that later on in another presentation. Altogether, we hope that with this project, we can contribute a little of making things more efficient, connecting connecting technologies and design employed with the supply side, the grid contacts to hopefully get better than what we're seeing in this upper process line and coming to more efficient solutions you're seeing down here. The objective we're following in the project, you can see here, is that the activity is to identify and support implementing the potentials of lighting that covers electric lighting, facade daylighting, and passive solar, and the decarbonization on a global perspective, while aligning the new integrative understanding of human lighting needs with digitized lighting on a building and a building-related urban scale. We have cast this objective, the scope, into this structure you're seeing here. We're organized in 4 so-called subtasks. The first subtask is on scenario strategies, roadmaps for decarbonizing, for reducing the carbon footprint. The second subtask is on the user requirement side, addressing specifically visual and non-visual aspects, quite research-oriented. Then we are having subtask C, which is on digitized lighting solutions, here covering, on the one hand side, the technology as well as design tools and processes. And subtask D is then verifying, hopefully, new concepts, or also maybe falsifying concepts which are out there in case studies and field studies. So that is how we are set up. And we are a group of around 50 participants, 50 active experts from altogether 15 countries. And I think we are with like 20 entities from universities, from research institute, but also from practice from private companies. So it's an international group, really going from North America up to Asia to Australia. So basically covering the perspectives of the whole world. I would now like to give you a brief, closer insight into this subtask A, which Lu Tao from CABR from China is running together with me, and a little support from Victor Ferreira from Spain. And here we first of all started with an analysis of what the status quo of LCA in lighting is. We generated an overview on data, methods, and regulations which are out there. The report is published. You find it on the website of our project. We have in this report a survey which we conducted in 15 countries. You get here ideas like the level and kind of LCA used in the different countries. We see how authorities support these processes, and also indications on more political level, how CO2 pricing is conducted currently in the different countries. The literature survey is based on a detailed review of around 60 papers. It is covering, on the one hand side, components, but as well case studies where LCA processes have been investigated, covering electric lighting as well as the daylighting side. Then we quite deeply looked into the components, EPDs for luminaires. Here as an example, we tried to understand the impact of energy mixes. You see this in this upper right chart, basically the relation in blue box plots of embodied carbon to operational carbon in the red box plots. Of course, depending on the power grid you're connected to, we identified the impact of luminaire design and tried to classify that in a certain way. One aspect which pretty strongly came up during the project is on simplification approaches. We learned that these EPDs are quite complex. They are in parts quite expensive to generate. And we see sort of not the ideal transfer yet into daily design practice, and tried to connect here and align a little stronger with the lighting energy rating methods which are out there, which are in many countries already established very well, and here try to go basically a quite similar way in providing generic energy product data for energy ratings. We would like to do something like that for energy life cycle product data as well, basically simplifying the processes. That's on the designer side. On industry side, from members in our group and also from exchange with companies, we understood that we have to look into more simple models in order to get these GVP values on a wider spread basis out into practice. So that is addressed as well. And here we are trying to address the market with a position paper, which is currently drafted, probably available during summer, fall of this year, where we're trying to especially elaborate on the SME perspective of these issues. Just to give you a brief idea of how things are looking here, we are looking at different groups of luminaires, so fixtures, conventional mass-produced luminaires, fixtures for new lighting concepts, and then the whole area of retrofit relighting concepts we're seeing, and trying to identify from data analysis here aggregated generic values for these subgroups, which then can directly be used by designers in practice without going into specific luminaires, which might not be known at the early design phases, for instance. Then also on the manufacturer side, how can these GVP values be generated more easily? We did some data analysis here, tried to set up regression models, and found that if we do correlations with like 5 different material groups, we get quite satisfactory results. So that can be a way in the future to simplify also that from industry point of view. The same applies for the facade components. We looked here into glazing and shading systems, try to correlate some performance indicators with daylight autonomy and with the embodied carbon, as said for the glazing systems you're seeing up here, as well as for shading systems, which you're seeing down here. That has been implemented into models. We are linking here the embodied carbon calculations with energy rating procedures, and that puts us then into place to do overall ratings in a room and a building context. And you can, for instance, identify by this what higher lighting comfort, for instance, raising the luminance level or going on to higher CRE levels, what impact that will have on the embodied carbon and the operational carbon, so the carbon footprint of the buildings. So then I would like to jump back to the overall perspective of our activity. As said, we are coming slowly to the end of the project. It's running throughout this summer. So the deliverables are now just being generated. There's a close link to standardization, so we have been involved in that. We are having several reports which are going to be published. Having guidelines out there, position paper which will be drafted. We are having a call open currently in building and environment on this topic. So that's a special issue which is being worked on here, and so I think it's open until the end of September. So if there are researchers here in the audience, please feel free to look at that, and maybe you find a contribution here for this special issue as well. So that brings me to the end, to the last slide. If you would like to follow how these deliverables come up, please visit us on our website, which you find above there. So thank you very much.
Super, Jan. Fast and a good overview. I think what is really impressive about your task that there are researchers and industry working together. I think that is very visible if we look into what you did with your white paper and your political statement on complicated EPD certification. Maybe we can go back to this in the Q&A as well at the end. Thank you, Jan. And please, our participants, there's a special Q&A button here in the bottom of the screen, and you can use it, type in your questions, and we will have it addressed in the Q&A at the end of the speakers. So in this, I would like to introduce the next speaker. Let me share my screen and get back to where you are here. Thank you for giving me, let me see, because I want to introduce the next speaker, which is Mandana Kani. She is director of the Master of Science in Light and Lighting and a lecturer of daylighting and lighting both at the Institute of Environmental Design and Engineering at the University College in London. She focuses on human health and well-being in indoor environments and the appropriate use of lighting and daylighting with a human responsive approach. Her PhD topic was on daylighting and visual comfort. And her topic for today's speech is visual and non-visual lighting requirements for decarbonization, collected scientific evidence and emerging insights. So, Mandana, I'm looking forward to your presentation and give you back the screen. Yeah, perfect. Yeah, you have to go into the presenter mode and unmute yourself. Oh. First, it's good to unmute yourself before you go into the presenter.
Yes,
Yeah, perfect.
yeah, I tried to do that, but it was
yes,
perfect.
Exactly. You cannot
Okay,
find.
finally.
Yes.
Thank you for this introduction. Yes, my presentation is about visual and non-visual lighting requirements for decarbonization, which is the scientific evidence and emerging insights that I would like to share. And as was mentioned already, this is part of the collective work and part of a subtask that was subtask B, and it was led by myself and Professor Barbara Matushak from TNU. When we talk about visual and non-visual user requirements, we of course refer to exposure to light, which is as part of a multisensory experience of built environment, or more specifically indoor environment, is affecting us in various ways. So what our body sees or what we see. And the objective of this subtask has been to identify and address the visual and non-visual requirements related to light as part of this experience. It has been the major objective has been to gather the latest knowledge related to decarbonization goals. In other words, we could and have been saying that we are playing the devil's advocate in this task. And by that, I mean that we have been trying to answer this question. Are such requirements aligned with decarbonization goals or not? In a general term, we have managed to gather, or as the major collective effort is still in the beginning and still at the end, what we think is that the various research directions are still needed to better understand the visual and non-visual user requirements and thresholds that need in the design and operation of buildings. But at the same time, I could present some emerging, in particular, five balancing relationship. which would define the relationship between the visual and visual requirements and the decarbonization goals that are in question. It is important also to consider that visual and visual user requirements are personal exposure within that we as humans are exposed to our environment in a multisensory environment, but it is in connection to indoor conditions. There are also control strategies to consider that are in play and system technologies as well. So in general, the point here is that it is a complex understanding to be created. So go back to the emerging insights, and this is part of one of the disseminations that we have, which Jan presented, shaping through a publication on a 10-question publication, so to say. We have tried to condense some of our findings into these 5 balancing relationship. The first one is focusing on daylight and view access versus overheating. So this relationship, which would mean more daylight, but can increase solar gains, overheating risk, and glare. In particular, here the outcome, the carbon or operational carbon outcome of this could mean is that we might have a decrease in terms of savings from daylight, which will result in extra cooling and lighting need, or increase in terms of cooling and glare reduction, which will savings. The next balancing relationship that can be mentioned is air control versus.
Mandana, do you think you can close your video because you have disturbance in your speaking? I think it might be if you close your video, it getting better.
Is that better?
Well, let's see, because every 30 seconds your voice is gone. Let's see.
Oh, sorry about that.
Okay, go ahead.
So do you hear me perhaps better now?
Yeah, just go ahead. We will see.
Okay, so the second balancing relationship that we can mention is glare control versus daylight availability. So glare protection improves comfort and reduces cooling loads, but decreases daylight availability and increases reliance on electric lighting. So here the outcome would be can be decreased in well, basically meaning that cooling savings will dominate reduction in lighting energy or an increase. So lighting penalty dominates cooling savings. And the third balancing relationship, visual task lighting versus circadian effective lighting. Standards target horizontal illuminance for visual tasks, but non-visual responses require exposure, and appropriate spectral time. So more specifically, this might be likely to increase operational carbon, especially when electric lighting is used to meet in deep planned or poorly daylit spaces, or may decrease operational carbon if daylight and efficient lighting strategies meet both visual and non-visual needs effectively. Be the circadian timing and spectrum versus operational carbon. So biological effective exposure might affect in specific time of the day, as a specific time of the day. And this timing may affect the dynamics of the energy grid and the carbon grid, so to say. So, meaning that the outcome would be that it may increase operational carbon or may decrease operational carbon, depending how the design has been. Finally, adaptive and responsive lighting versus person control. Here, of course, one of the emerging insights would be controls and responsive lighting, which can help increase occupant comfort. In certain cases, it can help to reduce energy as an so giving and of course decrease of satisfaction and agency over the space. However, it is by and in some ways it also may lead to higher energy use or greater variability in operational carbon. So again, in terms of outcome, it could have positive or negative, or it may increase or decrease the operational carbon. So these 5 insights will be explained in more detail in one of our publications, but overall, the overall conclusion is that the lighting and daylight strategies can both reduce and increase operational carbon depending on how visual and non-visual requirements are delivered. The operational carbon impact of occupant-centered lighting is therefore not determined solely by lighting energy demand, but the interaction between daylight availability, facade design, glare control, circadian timing, behavior via personalization and agency, and temporal dynamics of the energy system. Another point is that circadian effective lighting introduces additional spatial, spectral, and temporal constraints because biologically meaningful exposure must occur at specific times and often requires higher vertical monopic illuminance. Consequently, strategies intended to support health and well-being may conflict with decarbonization, at least with the strategies that we have now and with the findings and our knowledge currently, or demand flexibility goals in some contexts. At the same time, what we can say is that integrated daylighting, facade lighting control, and personalization strategies that were mentioned in these 5 emerging insights may provide opportunity to simultaneously support well-being and operational carbon reduction if designed holistically. And future progress depends on interdisciplinary approaches that integrate human health, behavior adaptation, building performance, and time-varying operational carbon within unified frameworks. As a collective or collected scientific evidence, we have put together the insights from multiple studies, and this is how we are imagining it to look like. So this is not still available. However, within this collection, a book of collective scientific evidence on visual and non-visual requirements, we have included 6 main parts. On part 1 is on visual stress mitigation and mitigation, a collection of studies that are research that are on improved understanding of the visual environment for humans. Part 2 is specifically on window view as itself and quality of the view, and relationship between window view and urban morphology. And part 3 focuses on non-visual effects, where again, some of the new developments in visual, non-visual aspects are put together, as well as measurement and assessment methods of non-visual aspects. The 3 last part focuses on digital tools, case studies, or a case study that would show some of these aspects, and carbon footprint that is sort of a connection between our findings and subtask A that was presented. A quick overview or perhaps mention is there's several studies or people that have and institutes that have been behind some of these studies. As mentioned in part 1, improved understanding of visual comfort for humans is collected studies of multiple ongoing research. The view preferences and descriptors for room with different visual stimuli and activities are addressed by, again, a collective work of multiple researchers and institutes that have been participating in this task. Relation between window view and morphology. And finally, we have new developments for non-visual aspects and measurement and assessment method of non-visual aspects, which are, again, done while across multiple collaborations, but led by different institutes, which are presented in these slides. And here are all the researchers that have been not only collaborated in general context of the task, but also mainly supported this subtask. And with that, I would like to close my presentation. Thank you.
Thank you, Mandana. I think this was an interesting insight into how user perspective influences light and light research. I think it's a complex field. Thank you very much for sharing this with us. So we will go now to the third speaker, and I will present, I will share again my screen shortly. So we are now at David, he is next. David Geisler-Modoro. He is a research associate at the Unit of Energy Efficient Building at the University of Innsbruck in Austria since 2023. After completing his doctorate in the technical mathematics, David Geisler-Modoro worked for 12 years as a project manager and head of the competence field Daylight at the Austrian company Bartenbach. So he combines, interestingly, both industry background and research background. And his topic today is digitalized lighting solutions, state of the art in technologies and design workflows. So, David, the floor is yours.
Thank you very much, Barbara. I will try to share my screen. Yeah. Thank you very much for the kind introduction. I'm David at the University of Innsbruck now, Unit of Energy Efficient Building, and I was glad and still glad to lead subtask C about digitalization in lighting in this task 70. And I just would like to give you an idea of what the project, our part project was about, and give you some results that we could gain during the last year, or the last 3 years in the project. Okay. So what is it if we talk about digitalization in lighting and daylighting? And how does that connect digitalization and decarbonization? So we're discussing and looking into different topics that we need to think about here. So of course, we start with thinking about digitalized lighting solutions for electric lighting and daylighting. So it's really the core technology, it's the systems, it's the products that are integrated in the building, that are installed in the building. Of course, if we especially think about facades and if we think about daylighting systems, we also need to think about how does that connect to our energy transfer into the building? How is the solar utilization? How does that look like? How is it connected with the HVAC system inside? And of course, also look into struggles and the issue of fighting for facade area, if we think about building integrated photovoltaics, for example. all these systems, no matter if electric lighting or day lighting, they need to be controlled to adapt to what we heard from Mandana, to react to the user, to provide what the user needs for specific times and situations. So we need to look into controls. And not only controls for every single system, but also connecting the controls in the building and in the bigger system, where the password, the keyword of Internet of Things comes into the play. Then we, of course, need to think about how does that work in the planning process. Jan showed this nice digitalization pathway, where a big step and the very start of it is in the design phase, where people start thinking about the solutions, start thinking about facade and lighting concepts. And nowadays it is standard to do that in a BIM-based workflow, so have a BIM model available where all the systems are in there. So we had to look into what is the situation for lighting and daylighting systems in the BIM workflow and BIM process. If we have a digital model, we then also need to evaluate, do we meet standards, do we meet codes? And for that, we have our simulation tools that can do lighting simulation, can do daylighting simulation, but they also need to be extended, they need to be further developed to also be able to do that for the non-visual requirements that users have, and also to connect it to lifecycle analysis evaluations. And finally, we need to tell the story. If we do the simulation, we need to tell the story to our client, to the architect, to the building owner. And here we looked into the virtual reality and augmented reality world as a novel idea of transporting the ideas and the projects and the processes that we set up. So in the end, it's clustered in two main areas, in two main regions that we have in that work that we did in technologies and systems, and in the process and design tools world. And for both of that, I would like to give you some insights into specific results that we could gain over these years. The project, as I said, is split up in these two areas, technology and design tools and processes. And I was happy to lead that subtask C that we had in task 70 together with Eleanor Lee from LBNL in the US. And we were in charge of putting together all the contributions that, of course, it was not the two of us, but it was the whole group, all of the experts working together here. So let's jump into some of the results and of the topics that we worked on during these years. Looking into technology, if we discuss technologies, for example, for facade solutions, they are, at least in the history, there were huge installations with a lot of steel, with a lot of aluminum, with a lot of material included there. But to bring that and to decarbonize also this approach and these solutions, we need to think about how can we put that into, let's call it micro-optical systems, include that in films, include that into smaller material requirements for these systems. So first thing we looked into the application of microprismatic materials for such fenestration systems, for facade systems, for daylight redirection, and investigated here what is out there, what are the processes to make these systems, how can they be used, and how can a roadmap be defined to select these systems for implementation in the building. Colleagues from China led this work here, who are also very active in our project. Of course, if we have systems like that and we finally think about integrating them in simulation work, we need to have data to describe them. We need to have the characteristics of these systems that we can include them in our simulation data. And this is where the so-called bidirectional scattering distribution functions come into the game, where we say we need to have this photometry of our daylighting systems and we need to describe that. For electric lighting, this is pretty much standardized. We do have our luminous intensity distributions for lighting systems, for electric lighting systems, and all manufacturers provide this data. But for daylighting and shading systems, we are not there yet. So this images only quickly show what is the basic idea behind the BSDF. It's really replacing the geometry of your system with the description of the lighting characteristics of the system. And with this data at hand, you can use it in lighting simulations then. Jan mentioned that at the beginning, that we are really also strongly involved, and in this case even leading the standardization effort for standardizing these kind of data generation for these BSDF data sets. It is linked to the standard that Jan showed, the 10916, which is dealing with evaluating the daylighting effect on electric lighting energy use. And there a method is described that uses BSDF data, but we don't have BSDF data generation standard at hand now. So this is what we did during the last years, also pushed that forward, and we're happy that we are now at the status of a draft international standard already, and looking forward to getting that published within the next year. A very short look into what is in that standard. We define how can and how should BSDF data be generated for daylighting or shading systems, and we split that up into microscopic systems, which is always, we call it microscopic whenever you can use it in a goniphotometer, so it's measurement based, which gives you a workflow how to do that. And for macroscopic systems, which have a bigger representative area, bigger representative structures, you cannot include them or install them in your goniphotometer measurement device. You need to do simulations to come up with the data. And of course, if you have a system like that and you have a complex surface material, you might even combine both to measure one representation of the surface and use that as input in your simulation. Going further, if we have the data and if we can do the simulation, of course, we need to, maybe we ran the simulation in the design process. We know we want to include that. We need to define that, and we need to define these systems also in our BIM workflow. And so we did a lot of work also investigating what is the current status on the one side in academics, in the scientific world, and on the other side on the market. So looking into what is the market demands, and on the other side, the scientific world, looking at this topic of BIM workflows and where are the pain points in these BIM workflows when thinking about electric lighting and daylighting systems. And here it was very interesting to see that it is depending on which parts of the life cycle in the building, if you want it like that, it's in the design or in the R&D, or then in the manufacturing of the products or in the facility management in the use case, where the data can be used way more or is already used way more. And then the other side, if we look on the top right side, the graphic, the advantages and disadvantages and challenges of the use of BIM, we see that the main challenges are due to insufficient personnel and costs and time to do that BIM planning. And on the other side, the advantages are clear in that it's more efficient to use it, and the transparency and coordination efforts are lower, and thus there is a high advantage there. We took that and together with the informatics department here at the University of Innsbruck, we then went ahead and said, okay, what is missing to come over these pain points and to help designers also to work on that. So here a so-called middleware was developed, which helps to prepare everything that you plan and you design your control system in your BIM workflow already, but auto commissioning, really getting it into the building then is usually, there's a hard break. Usually do the design, you specify it, and then it is installed and everything is done again. The control is programmed again. And to overcome that and to avoid this break in the workflow, this middleware was developed that allows you to already define and program that once in the design process, and you can directly implement it on your system in the reality. talking about the simulation, and we heard from Mandana that the non-visual requirements are key, and we need to look into that. On the other side, simulation tools, they are usually made for visual evaluations, for lighting evaluations. So we need to look into that as well. And to do so, we need the spectral simulation capabilities of software. And the partners who were also a part in the project here from LBNL, who are working on the Radiance software, which is pretty well known for daylighting calculations, they worked on a hyperspectral rendering functionality in Radiance over the last years, and also did that within this task. So there is the feature now available that you can do full spectral simulations within Radiance and come up with all the non-visual evaluations that we need for evaluating the non-visual effects of lighting. To do so and to evaluate if you have new systems and new software systems available, you want to have reference rooms where you can compare your situations, where you can compare your software systems. For this, we defined together, Jan also showed that already for the LCA evaluation, but we also defined this in a full spectral mode, that we have reference rooms available that can be used by designers, that can be used by researchers or software developers as reference cases, and they will be made available with all the data that you need to run the simulations. And as we said, as a final part, if I have my simulation results available, I also need to tell the story. I need to present my results to the client. So we did a study on, again, looking into both sides, scientific world and market world, with a survey among lighting designers, how important they see the topic of virtual reality, how well they can use it in their practical work already, and how well it is done. And here we found that the main pain point is that it's not simple and intuitively to be used at the moment, and that there should be easier ways to connect it with your standard lighting design workflow to come up with these VR experiences. Also here from our subtask, and it's my last slide to show you, there will be reports summarizing all that. The things that I showed you, there are already scientific papers out there, but of course the key messages, they will be summarized in reports, which will over the summer also be then published on the task website. Here's the link up there as well. And finally, I'd like to thank also from the Austrian side, all the work that is behind that from our Austrian side. It's financed for our Austrian research funding agency. I'd like to acknowledge that as well, and thank the audience for listening, and I'm looking forward to having a nice Q&A session afterwards.
Thank you, David. This was interesting, seeing how you help designers actually work on this. We will discuss that maybe a bit later. Yeah, please, our participants, type in some questions. We will have one last, hopefully quick presentation, and then we will go to the Q&A. So let's see. I will introduce the last speaker and share my screen and see. So we have Nico Gentile with us. He is again a professor. We have very high level people here, an associated professor at the Division of Energy and Building Design at Lund University in Sweden, where he also serves as program director for the Master of Science in Energy Efficient and Environmental Building Design. His research focuses on daylighting and electric lighting in buildings, integrating buildings physics, environmental psychology, and architectural design to evaluate both environmental performance and human experience. And he will talk today about application and case studies. How do concepts prove in practice? So, Nico, you are the one to present.
Yeah, thanks, Berbel. And yeah, as you said, I'm gonna try to give a little bit of account of how to put concept into practice. So basically what we call it case studies, very simply. It's quite classical approach in IEA tasks. Just to contextualize a little bit the work that we are doing in the old task, we are speaking about sustainability, but what is sustainability in daylighting and lighting? It's of course environmental sustainability, so finding solutions that are good for the planet, and from there the name low carbon. And then we have another keywords in our title, high comfort. But that's nothing else than one of the other pillar of sustainability, is social sustainability. So we are trying to find solutions where lighting and daylighting can promote well-being, health. We know that we can do, and this is what we meant with high comfort. And I wanted to mention that because just 2 days ago, it was the International Day of Light, which exists since 2015, when it was nominated by the United Nations because of the role of light and lighting in the development of societies and communities. So we really have an important social roles as well. And then there is, of course, the economical sustainability, financial sustainability there as well. But jumping more specifically into what we are doing in our subtask D and which type of questions we are trying to answer, the first and main one I would say is, can high comfort and low carbon solution be achieved simultaneously? And if yes, which are the environmental impacts across different building scales? At the end of the day, we want to have some lessons learned about the social and environmental sustainable daylighting and lighting solutions. We're working at different scales, and together with my colleague Natalia Giraldo Vasquez from DTU Denmark, we are more focusing on the component, room, and building scales of solution, while we have much needed help from Justina Martiniuk-Peczek from Dansk University of Technology, who is focusing on the neighborhood scale. Basically, they're trying to look how urban densification, which is definitely a good thing in terms of environmental sustainability. We optimize city, less solar consumption, more optimization of space, so to speak. But this densification can reduce access to daylight, increase energy use, and therefore we need to look at the interplay between the two things. And it's, of course, not only 3 persons working there. As Jan has mentioned, we have the invaluable support of more than 50 global experts in our subtask, perhaps more than others, because we are collecting experience from other people, from all the experts there. What you're going to get, hopefully after the summer, on our task website.
Sorry. No, you were just interrupted, but it's back. The sound is back.
Okay, thank you. So we are going to have fact sheets for the component, room, and building scales, 4 or 5 pages PDF for each case study in a quite appealing, popularized fashion, so not for the scientific audience only. And for the neighborhood scale, we have something a little bit more interactive. Dansk University of Technology is preparing some web atlases where the target audience are mainly urban planners and also architects and practitioners. You can go there, see some case studies from different neighborhoods across the world and see how daylight and environmental aspects are playing together. Let's jump directly to some examples, starting from component, room, and building scale. It's a small selection of over 20 case studies that we have. The first one that I want to mention is a low carbon example, electric lighting from Norway. It's Biljana Obradovic, in this case, who was the expert providing us information. It's about upcycling of lighting system. What they did, this is an office in Norway, Norconsult. They used the previous housing for T5 fluorescent lamps replaced with LED, the light source, tried to reuse as much as possible of the housing, tried to play also with optics so that they not have to use new material, and try to compare life cycle assessment for this type of luminaires, installing them in their offices and check the global impact in terms of different impact category and also some feedback on quality from the employees. And easy to say, the impact of those upcycled luminaires was largely lower than buying a new state-of-the-art or best practice solution with a new luminaire, and it was widely accepted by the users. We have also another couple of examples of low-carbon upcycled luminaires from Denmark, and I don't remember which other country. If we move to daylighting system, here the question has been answered in Sweden with 2 excellent master students that are defending next week, Novia Stella and Anifa. They've been working on the question of shading devices. If we take automated shading device, most of us can agree on the fact that having automated shading, it's normally pretty good in an energy perspective, operational energy. But they asked the question, what happens if we take the whole life cycle perspective? Because for having automated shading, we are using energy and emitting carbon to create motors, we need sensors, we need a lot of other devices, and they will also use energy. They had a quite special case. It was a fully glazed building, so a little bit special in that sense. Long story short, in this specific case, also in all life perspective, the global impact of automated shading was largely lower than manual shading. Of course, I would be curious to see what happens with a little bit more standard rooms and standard geometries, but the main message for me is that we have to ask ourselves those questions. Another low carbon daylighting and lighting example is the newly built zero energy building living lab at the university campus in Brasilia. Claudia Naves David Amorim was supporting us with that. Long story short, very highly performing building in terms of operational energy use. The total global emission actually good, but not that excellent. Main message again, we need to increase our perspective to our all life aspect. Then let's start to combine low carbon and high comfort aspect. We have a study here conducted by Pauline Karstes and Luca Focus last year in Denmark, 2 master students from our master in Sweden. They took a quite common example. There are a lot of industrial buildings in Scandinavia that have been reconverted or are on the way of being converted in offices and in residence. It's called adaptive reuse. And they said, what happens when we do the conversion and we try to comply with the Danish building regulation, which is one of the most challenging or advanced, depending on how you say, on both daylight and environmental impact. They are quite strict and they are increasing and making rules even stricter across the years. They tried many different, let's say, design solutions, actually several hundreds. Long story short, I plot on the y-axis here the global warming potential of different designs. So every point is a different design. We have here, so the lower the better. And on the y-axis, we have, let's say, daylight autonomy or daylight penetration. So the higher, the better. And the lines here, dotted lines, are the different requirements that we have in Denmark at the moment, and then what we will have in the future years. So if we look at the sweet spot of compliance, we see that less and less cases will be complying with both the daylight and environmental regulation as we go ahead with years. And finally, if we move to pure eye comfort, we have several case studies mainly focusing on integrative lighting, so circadian requirements. Mandana has been speaking a lot about that, so I won't focus on that much, but I can say, once again, daylight is very important to reach those new requirements, circadian aspect. We move there to the other scale, neighborhoods and overview. Here it's a little bit more difficult to give examples. I can just mention that we have over 20 case studies from all over the world. Web atlases will be available, and you can check there how daylight and environmental impact, their interplay. So in a nutshell, just to conclude very rapidly, some general lessons learned. When it comes to electric lighting, upcycling is very promising for reducing embodied carbon. When it comes to daylighting mainly, and what we call high comfort and low carbon, they can be achieved simultaneously, but it becomes harder and harder. And we have to look at always them together. And the requirements for integrative lighting, circadian lighting, they call for innovation in lighting and better daylighting. So this comes quite clearly. So in a word, there are some challenges ahead, new requirements and challenges ahead means innovation. So innovation is calling, and I think this is very good news. There is a lot to innovate in the fenestration or window industry, in the facade industry, but also the lighting one. So thank you.
Wow, thank you, Nico. I know from the past that this is a lot of work working on these case studies because you have to do a lot of data gathering to get these 4 pages together. Nico, how about the implementation rate of these case studies? Are these mostly research-based case studies, like you mentioned, some where studies were made, or are most of these case studies implemented one and you also have feedback from the reality world,
No,
performance data?
Yeah, we have some feedback mostly on the electric lighting part because there's especially upcycling of luminaires that's quite mature. So we have good examples. For the daylighting part is much harder because projects takes much longer, and also it's very difficult in real project to extrapolate the role of daylight in decarbonization. So normally you have LCA for the old buildings, so a little bit comparing apple and pears. So what we have mostly are real case studies and then different scenarios that we try to define. So the numbers comes from scenarios based on actual based case studies, so to speak.
Okay. And how about between retrofitting and new buildings? Because I can imagine that your work is much easier in new building than it is when you do a retrofitting situation.
Yeah, again, when it comes for daylighting, I would say retrofitting is actually the main, because if we look at your building, there is the all embodied carbon that goes to the building itself. So actually one of the main conclusions that we see there is, doesn't matter. Beside daylight, if we want to build environmentally friendly, we have to renovate. So that's the only thing. It's much harder with newly built stuff. And we have actually, outside this task, but for other works that we do, quite many, let's say, carbon neutral buildings that are actually have quite a lot of embodied carbon as well, even if they are carbon neutral. So it's a little bit renovation, I would say.
This is the main. Okay.
One message is renovation. And then
And
there is also, even with glazing, renovating existing windows, if we focus only on that, that's main, because glazing, it's quite energy intensive, the production, and also the recycling, not always easy.
Yeah, this was a new subject to me, Jan, that you mentioned in terms of recycled glass and low carbon. You said this is reducing the glass carbon content by, let's say, 40 or 50% even, if it's recycled glass. How does it work?
Yeah, it's like 40% down, yes. So it's one of the or maybe by now even 2 big manufacturers, they offer these products.
And they gather existing, or they put window glass, they take it back sort of,
exactly,
and this is and they
add recycled glass to it. Yeah, exactly.
Add recycled glass. Okay. So we have a question in the chat here. I think it's for David. Yud Karma is asking, how does the glare estimation tool help designers balance daylight access, visual comfort, and energy performance?
I read the question. I am not 100% sure what it is aiming for. So I give a maybe too general answer, but I try. Of course, it is always in the simulation tools, you always have to have the chance to do all of the evaluations. So that is glare, but you have to do daylight sufficiency metrics. You do have the daylight availability in the room. Visual comfort is glare. It's usually what we talk about, glare. And energy performance is usually then done in the next step to estimate, okay, what is the impact of the design solution for electric lighting energy or for HVAC energy, heating, cooling. And of course, it's also then a question of how you put your how you rate the different items that you have, because usually you say, okay, glare, you have limits, and that is a no-go. You have to have a glare-free environment for an office building, for example. And then the next step is, okay, you can optimize everything around that is optimal in energy performance best possible daylight access, but still, if you need to have it glare free in the first case. Otherwise, you are not even allowed to build it like that. So it of course helps, but maybe one answer to that is a tool and a simulation software is usually something that helps you evaluate, but it doesn't provide you the design idea. So this is something that is maybe important, that also the evaluation tools, they are to certify that you did a good job, but not that they give you the idea how to solve your building.
Mm. You mentioned in your presentation the digital twins as a tool to optimize lighting systems. Is this something which exists in the research arena, or is this something which has actually arrived at the designer level, niveau, sort of?
Both. It is still ongoing research to like push it even further. And for example, we here are running a project on reinforcement learning for lighting controls, so that the system itself learns to be more efficient, to provide without less errors the intended lighting situation. But the digital twin is already in a way implemented. It depends, of course, on the type of building and on the facility management. But there are many facility managers out there. They are using digital twins. They have live data that they can use to further improve their systems.
Okay. So is there, like, I know this from solar district heating, that there is really like a new industry or service companies are popping up and they have lots of stuff, you know, and they are offering district heating providers their digital twins, and it takes them a year to work in parallel, and then the digital twin takes over. Is this a scenario which might also work in lighting, that the digital twin will get more and more intelligent by analyzing the data from a huge building and then takes over? Or is this doesn't work because there are too many people involved in using the rooms, or is it?
I'm always hesitant with the saying it takes over. I think it is still a facility management, and it's of course like very much supported by that. And there's maybe there's then not 5 people working it, but there's 4 AI agents and 1 person. But in the end, if it really takes over, I doubt it that it will be very soon, but yeah.
Okay, you are rather doubting here still. So in general, I would like to know if you look into this, maybe to Jan, this long work of more than 10 years in lighting, where is in the globe, because you have partners from China, Australia, Europe, I don't know about America, North America, where is demand for these new luminance and new lighting systems? Where is it popping up more, and where it's because it's a well, efficiency and decarbonization strategy, which probably is interlinked to policies as well?
Well, I think very frankly, it's needed everywhere.
It's really,
I mean, I mentioned in the beginning that the increase in lighting consumption is like at 2%, I think, globally, but you can differentiate that between Europe and other parts of the world. That's quite interesting. They identified that from satellite image analysis, and so Europe obviously is the lighting intensity is actually going down because we are using a little more let's say advanced candle power distribution, things like that. And in the Asian region, you're still having economic growth, which of course fosters that, but it's in some places, I think there's still room for applying more of the new technologies. Yeah. So I don't know if that answers a little the question. And I mean, it's lots about in electric lighting, I think, about industrial processes and economies of scales. I mean, that is what we have seen all over the place. That is, it is a much more integrated product we're seeing nowadays. They are highly efficiently produced. interesting what we learned when we were in China last fall, that 2/3 of the world lighting gear is coming out of China by now. Yeah, so that is basically the spot
Okay.
to look at where the stuff is coming from, and so. Yeah, I mean, I mentioned it from the lamps itself. I think we are at the physical boundary of like 200, 210 lumen per watt for white light we are getting. So that is so no more potentials there. It's more about the luminaire architectures, about the lighting concepts where we are still seeing potential. Yeah. And I mean, there are a lot of lots of little tweaks where you can adjust and optimize things, of course, but yeah, it's
Interesting. If I hear about your task, I always think about these huge facades in Asia with the skyscrapers, and they are all in red and blue, illuminated, and so on. Have you studied whether these are also nice bulbs in the meantime? And is it efficient lighting, or is it still just blown electricity to the
Wow.
for
Yeah,
the
I mean,
night?
it's looking impressive, and
It looks very
in
impressive,
some
yeah.
places they are running videos across the skyscrapers, very impressive. But of course, it's an add-on. I mean, even if the LEDs are highly efficient, it's sort of a rebound effect. We're doing things with LEDs which we have not done before because we
Or
couldn't do them with a former technology. So. Yeah, but
so it's still
it's not only efficiency lighting, it's architecture, it's well-being, it's communication at that point. So we
yeah,
just have
yeah.
to accept that. Yeah.
Maybe we just have a quick look into what you talked about, the EPDs and your white paper. So this is only concerning Europe, I assume, or it's not a worldwide topic, huh? It's only the European regulation which causes these extra workload on the manufacturers of aluminums.
Yeah, I mean it's not all over the world mandatory, not in Germany or in Europe either. It
Oh,
is slowly getting there. It's not like energy regulations at the moment. Yeah, but if you're looking for specific funding or subsidies for high advanced buildings, it is getting to the point where it is requested. So it's an issue. And we are seeing that big industry, big lighting companies, they can attack that much easier because they are having ERP systems. They are having much bigger product lots than comparing that to small and medium companies. They don't have this digital setup. They have to collect many more data, and they only have, I don't know, maybe 100 or 200 or 1,000 fixtures of the same types they're selling at once. And so they're getting an extreme overhead by these EPDs to the costs they already have. Yeah, so that's quite a thing. And we made together with a partner company some assessments that you find these EPDs for big companies. They publish them by now. But the smaller or medium size, up to what did we look at? Up to 500 employees, something like that. They are basically having none. And so
okay.
once you're getting at the point that it is requested for some building certificates, they have a big disadvantage, and that is something we have from the market perspective look into. Yeah, so too high complexity and trying to. Yeah, based on lots of data which have been collected to come up with some simple models and some aggregated values, which will help everybody. I think will give a general push on getting lower embodied carbon into the market. Yeah.
Okay, good. Yeah, thank you. We have seen a really big overview of technical issues, user issues, use cases. So we wish you good luck for finalizing the task so that we can see a lot of these nice announced publications finally on your website. And yeah, I will hand over to Ellen for the final words and thank already the speakers and the participants and wish everybody a good rest of the day.
All right, yeah. Thank you very much, Bärbel, for your great moderation. And thank you, of course, to the speakers for their presentations, as well to the audience for participating. To wrap things up, We have recorded today's session, and we will make the recording available to you on the ISIS YouTube channel and also on the IEA SHC Solar Academy homepage. The same also goes for the presentations that you have seen. They will be made available as PDFs, so you can download them and browse through them. And for our ISIS members, I would like to remind you that you have unlimited access to all past webinars and presentations through the ISIS members area. And for everyone who's not an ISIS member yet, we invite you to join us and to share our mission. And then finally, as I have mentioned earlier, I would also like to invite you all to join us in Freiburg in Germany this September for Eurosun 2026. Ticket prices are now online on eurosunconference.org, and it will be possible to register in the coming days. So stay tuned for that. And so again, thank you everyone for joining and participating. And we are looking forward to meeting you at the next webinar and see you soon. And we wish you a pleasant rest of the day.
Yes. Bye-bye, everybody.